Hey Year 12, welcome back after some technical difficulties. I am here with the second part of this exercise, okay, where we are applying some of these new skills that we've got differentiating exponential functions. Right? We've done some changes in normals in that previous example. Now we want to look at sketching some functions. Right? You've done lots of function sketching before. You have various steps that you'll follow along the way, and we're just going to do the same things. It does involve a little bit of differentiating, right? First and second derivative, important tools in sketching a function. So we'll have to do that as we go along. Other than that, right, the same things as you've done before. So first of all, the domain, right? There are no square roots or fractions to deal with here. So the domain is all real x. Right, easy. I've got to write small because this takes up a lot of space. B, test whether the function is even or odd or neither. Neither, we took a look. Function, negative x, right? Replace the x with a negative x, and I get negative x e to the negative x. Is that the negative of my original function? No, it's not, because that negative here. Is it equal to my original function? No, it's not. It does not equal function x. It does not equal negative function x. So therefore, neither odd nor even. Neither odd nor even. Fair enough, you've done that before. C, find any zeros of the function and examine its sign. Okay, well, if I substitute x equals 0 into that, let x equals 0, I very rapidly find that y equals 0. Right? If x equals 0, y equals 0 very quickly. If I say y equals 0, well, once again, I can pretty easily say that is only going to happen when x equals 0. There's just that one intercept there. It passes through the origin. But I do want to know a little bit more about it. If x is greater than 0, what happens? If x is greater than 0, I have a positive number raised to some power. Doesn't matter. It's just going to be small. I get a positive number. If x is negative, I get a negative. Right, so if x is greater than 0, y is greater than 0, x is less than 0, y is less than 0. Okay, so we know that this function is going to pass from the third quadrant up into the first. Right, third and first. C. Okay, move along to D. Feels like we're near the end, but there's quite a lot to it to go now. Examine the behaviour as x approaches infinity and x approaches negative infinity. What happens out on the wings there? This part is tricky. So we are told that as x approaches infinity, the function approaches 0. Okay, because what's really happening there is I have a number that's really big multiplied by a number that's very close to 0. And that can be tricky. Right? That's not straightforward. Big number times big number is big number. Small number times a small number is a small number. Big number times a small number could be anything. So we're told here that it's going to approach 0 when that happens. So let's just write it as limit. Limit as x approaches negative infinity of x e to the negative x. Right, as it's negative infinity, I get a negative infinity. Okay, because this becomes positive, so I get e to big number multiplied by a very big negative number is negative infinity. Okay, so that's my third quadrant. Right, just keeps pushing down there. We also need to know the limit. Hey, what happened there? The limit as x approaches infinity of the same thing, x e to the negative x. We are told this, that is equal to 0. Okay, so it's a bit weird. Examine the behaviour, work this out, but here's a hint. There's part of the answer for you. So it goes. Part E really does look like we're near the end, but it's starting to get harder all the time. Find any stationary points. How do we find stationary points? It's not Officeworks. No. Stationary points is where the derivative of that function is equal to 0. Right, we need to find where the derivative is equal to 0. To examine their nature, we find the second derivative. We substitute in the x value there to the second derivative and see if it's positive or negative. It's concave up, concave down. So I'm going to say y equals function x for function x equals x e to the negative x function prime x I have to differentiate my function here. It's product rule, so we take the second part, e to the negative x, multiplied by the differential of the first part, times 1, plus the first part times the differential of the second part, which is negative e to the negative x. And I can take a common e to the negative x out of 1 minus x. Okay, so there is my derivative. The derivative of that function is e to the negative x outside of 1 minus x. Outside of 1 minus x. Now, what I need to do is, I want to find out where that is equal to 0, right? That's my gradient function, if you will. I want to find out where the gradient is 0, where the gradient, which is going to be where I've got a flat spot, a horizontal point on my curve somewhere, and I'm expecting there to be one in the first quadrant. So, let function prime x equal to 0, and therefore e to the negative 0, e to the 0 outside of 1 minus 0. Oh no. Sorry. Now I say e to the negative x, what am I thinking? Outside of 1 minus x is equal to 0. I'm not trying to find the gradient when x equals 0. I'm trying to find x where the gradient is equal to 0. So I've got these things. Now, a little bit of common sense here. I have a positive number. Remember, e is about 2.7. There is nothing that I could raise e to the power of that will make it equal to 0. So my null factor law, I've got two things multiplied together to give me 0. One of them, at least one of them, must be equal to 0. This can't be 0. 1 minus x must be 0. So x equals 1. That's the only thing that will make that 0. Okay, so let x equal 1. Therefore y equals 1e to the negative 1. Y equals e to the negative 1. So I have a stationary point. At 1 e to the negative 1. Right, there's a stationary point. But is it a maximum? Is it a minimum, or is it a horizontal point of inflection? Well, we'll need to find the second derivative. Now, function double prime x. Time to scroll, isn't it? Function double prime x is going to be equal to, again, I have a product rule. So I have 1 minus x times the derivative of the first one. That's negative e to the negative x. Plus the first one, e to the negative x, times the derivative of that, negative 1. Okay, and here I get, right, in fact, I think if I expand and simplify that down, I wrote it down somewhere just to save time. I'm not saving time now that I'm looking for that there. I get e to the negative x outside of x minus 2. Right, that's what I get. E to the negative x outside of x minus 2 once I expand that and factorise it again. So we have this. Now let, if x equals 1, what is the second derivative there? Well, therefore, function double prime, well, we said function double prime 1 equals e to the negative 1 times 1 minus 2. I get a negative 1, negative e to the negative 1, minus 1 over e. That's a negative number. That means it is concave down, means that I have a local maximum. That really makes sense. If I've got an asymptote that's the x-axis, already determined that, right, as it approaches infinity, my function approaches 0, and it's in the first quadrant, right, it hasn't crossed the x-axis again. Right, I know that it has started there and it's moving back. It's gone up. It's come down somewhere. There must be a maximum. Anyhow, we have examined the nature of that there. I know that there is a local maximum, so stationary point, maximum at 1 e to the negative 1. Righto, find any stationary points? Yes, we did find that and examine its nature. It's a maximum. find any points of inflection. Right, so for f, points of inflection are where our second derivative is equal to 0. Now, let function equals 0, therefore e to the negative x outside of x minus 2 equals 0. And again, e to the negative x can't be 0, so x minus 2 equals 0. So x equals 2. So I have a point of inflection at x equals 2. Now I should say function of 2 is equal to 2 times e to the negative 2, e to the negative 2, righto, or 2 over e squared if you like. But so my point of inflection at 2 e to the negative 2. Point of inflection's there. Now, we also know, okay, I know the second derivative of x equals 1. I know it's negative there. Okay, so I know that it has gone from being like this, and then I've got a point of inflection. If I were to substitute in something like 3 into this, what happens if I push 3 into here? I get e to the negative 3. 3 minus 2, right, that's 1. I would get e to the negative 3, which is positive. So, let's just draw this up. I'm going to say x and function double prime x. Little table of values, right? A little bit to determine the nature of this. Let's say we're going to have, we know what it is at 1. I know what it is at 2. And I've just substituted in for 3. We said at 1 it was equal to negative e to the negative 1. It's negative. Right, concave down. Here it is horizontal. Oh, sorry, horizontal here. Because I have... because at 2 it's equal to 0. Yeah. And at 3 we said that that was going to be equal to... we said that was equal to e to the negative x, which is positive. Right, so it goes like this. So I have my point of inflection here. I have my stationary point here, my maximum here. I have my 0 at the origin. Right? My intercepts, both my intercepts at the origin. Now, finally, alright. Well, let's just sketch that after doing all those things. Right? We've done all of those things. Let's sketch this thing. Most of the action's over here. X, y. Okay, we know that it does this, and it goes down over that way. Don't get, look, there's curve. It goes down, doesn't it? We know that. So here, and here at 1 and 2, we have something going on. We have our maximum here. Our point of inflection there, and our asymptote there. Right, oh man, I don't particularly like the way that looks, but anyway, this is going to be, right, that was at 1 and e to the negative 1, right, that's my maximum. Not very beautiful, but anyway, then right down here at 2 and 2e to the negative 2. Right, 2e to the negative 2 is going to be less than e to the negative 1. That is my point of inflection. There's my curve. Righto. There's a fair bit of work in that. There is a 14-minute video. Holy smoke. Right, that'll do it. Check it out. Watch it fast. See you later.